sketchy in your mind, although you've revised it doing forces last year. So motion, let's not worry about forces, just motion for a minute. The equations you need. Right, this is a revision session. I'm going to be pragmatic and just get down to business, right? The equations that you require for motion are 3 in number. A equals v minus u over t. And then this one, v squared equals u squared plus 2as. Now, this third one is probably the one that you've used least frequently because, just because questions aren't often asked about it. But let's just make sure we're aware of what all these symbols mean. S is used for distance or displacement. At IGCSE, you can just think of it as distance. V, final velocity. U, initial velocity. And A, acceleration. So which equation you use really depends, doesn't it, on what you're given in the question. So you may find, for instance, if you're given a distance, an acceleration, and an initial speed, and you're asked to find the final speed, you would have to use the bottom equation. Now, most of the time, in fact, all of the time, that's as difficult as it will get. Apart from, of course, knowing and getting your units correct, acceleration being meters per second squared, velocity being meters per second. Obviously, distance is meters. Okay, so those are the equations. We also need to be happy with the 2 types of graph, distance time and velocity time. Those are the only 2 types of motion graph that you will come across at IGCSE, and you need to be comfortable identifying the kind of motion which is being represented. So, for instance, a horizontal line is stationary in a distance time graph or for a distance time graph, but obviously, if you're looking at a velocity time graph, a straight horizontal line means you're moving at a constant velocity, say 10 meters per second. So you need to be very careful which graph you're looking at when you're looking at graphs of motion. Remember that you can work out different things from a graph. So a distance time graph like this, you can find the gradient of it. So the gradient, for those of you who've just arrived, by the way, you can use the chat if you want me to labor a point or go over something specific, and then I can sort of shape the session towards your needs. Otherwise, you can just listen. Gradient is the speed or velocity. Okay, at IGCSE, speed and velocity mainly are, you can basically use them interchangeably. Only when you're changing direction or going backwards do you need to worry about the distinction, but normally you can sort of think of them as being very much related, because they are, as we know. Speed, velocity is just speed with a direction associated with it. Usually we just take one direction to be positive and backwards to be negative. The velocity time graph, you can find the gradient, sure, but you can also do something else. So the gradient of a velocity time graph gives you the acceleration, so the slope, rise over run, is acceleration. The area underneath, which I'll draw in green, tells you the distance traveled. Now, when you did motion in the forts, you probably took about 3 weeks to go through all that and practice it. That's more or less force motion summarized in its entirety. I think once you've got the hang of finding gradients and using equations, I think looking back, that's fairly straightforward. So I don't want to dwell too long on that. In the removes, you then added to this, didn't you? Because you came back to motion and then added force into the mix and asked the question, how does force affect motion? So that's what I'm going to do below. Again, I'm keeping my eye on the chat, so you can make any comments to me if you want. So, force. I'm going to start with the equations again, or the equation. The equation that you came across in the removes was, I'm going to leave a space because the equation was force equals mass times acceleration. So that was our link between force and motion, right? In that objects accelerate when you apply a force to them, or a resultant force to them. So you could almost say here, you can have an imaginary or an imagined resultant there, because as we know, force does not necessarily mean you're moving. Because the first law, Newton's first law, says that if the forces on an object are balanced, so for instance, a book on a table, we've got weight acting downwards and the reaction force, what I call the normal reaction, because it's perpendicular to the table. Let's write that in. Normal reaction and the weight, they're balanced, right? The arrows are the same length. The book is stationary. Resultant force equals 0. That's also true of objects moving at a constant speed. So you need to be very familiar and comfortable with the fact that constant velocity, right? So constant velocity implies that the forces are balanced, right? So resultant force is 0. Now, you'll remember when you were in the removes and first came across that, it was probably something that you didn't expect. You probably thought that an object moving at a constant velocity, like a car bombing along a motorway at a constant velocity, there must be a force pushing it forward. But I always make people think of, like objects moving through space, right? They just move. If you throw a torch across a space station or in space away from any other big objects, it just travels in a straight line forever, right? Objects will move in a straight line unless acted upon by a force. Equally, objects which are moving at constant velocity have to have all forces balanced. So in the case of a car, the weight is balanced by the normal reaction from the road, and the driving force from the engine is actually balanced by the drag or air resistance. So that's Newton's first law, right? An object will remain. In fact, I might even write this down. And that way it'll slow me down, because it's very easy for me to get carried away and go too quickly in these sessions. So an object will remain at rest or constant velocity unless acted on by a resultant force. Okay, so very simple. It's remarkably simple, but it's actually very important, that is true. Next, then, this equation tells us what happens when there is a resultant force. So when there is, hello, Nick. When there is a resultant force, we use that equation. And remember, force is measured in newtons, mass, kilograms, and acceleration must be in meters per second squared if you're going to use that equation. This also tells us, and since you're fifths now, you'll have come across this relationship more frequently. This equation actually tells us that for a particular mass, for fixed m, the F is proportional to A, because this equation, F equals ma, is of the form F equals kx, or, F equals a constant times acceleration. So in fact, Newton's second law is basically saying that force and acceleration are directly proportional to one another. If you double F, you double your acceleration. If you triple F, you triple your acceleration. So you see direct proportionality it's amazing how it turns up so regularly. Why does the universe behave in such a simple way? Hopefully that makes sense. The third law is I could number these, I suppose. 1, 2. You don't need to remember which order they're in really, but every action has an equal. Now, okay, I'm just going to write it. I don't like this way of writing it, but this is considered okay by everyone. Every action has an equal and opposite reaction. So if I punch the wall, then I exert a force on the wall, but my hand also feels a force from the wall. If you've been doing gas laws recently, and you've talked about pressure in a gas, you will have discussed, or you will discuss if you've not, when a molecule bounces off the wall and changes its velocity, it applies a force onto the wall. But because of Newton's third law, we also then say the wall pushes back or exerts a force back on the molecule. So you can use Newton's third law to sort of discuss pressure in a gas. You can use it to explain why your foot hurts when you kick a football, or you feel a force on your foot when you kick something. So again, by now, I'm sure that one has been ingrained into your memory, probably, for most of you. So that's Newton's third law. Now, in order to discuss forces, because I can discuss all of these things really, I'm going to use a very particular situation which you're all familiar with, and that is someone jumping out of a plane. Because the reason that's a brilliant example is that it contains almost everything you need, every concept that you come across in forces, right? Acceleration, balanced forces. You can even think about velocity, what's happening to the velocity. So let's do this. Now, my first drawing will include a plane with a person at the door. Now, imagine they jump out or they step off. Initially, I'm going to now draw this man as a dot, right? So that's the man or the woman, right? Just the person. So initially, they're not moving, are they? Imagine they just step out, or the hatch opens from underneath their feet. Only the weight is acting downwards. Unbalanced force. So the person will, and again, let's draw the graph underneath, shall we? So this is velocity, and this is time. So initially they're at rest. So I'm going to draw a big X there. But then they accelerate, don't they? Because the weight is acting downwards. So the acceleration is going to do this, cause the velocity to increase. But the force that starts acting on them upwards, the drag, once they start moving, once you move through air, you experience air resistance or drag. So the weight will still be acting downwards, yes? W. But now we have to draw, and it will be the same size as it was before. The weight doesn't change. Appreciably, anyway. The drag will start acting upwards. So the resultant force downwards, if you take the weight and then subtract off that little bit of drag which is formed, then the resultant force downwards goes down, right? So resultant force decreases, which means the acceleration downwards decreases. So he's still speeding up. It's just that the acceleration will get less and less. So as the drag starts to act, the slope of this line will do this, because as drag starts to act upwards, the resultant force downwards is lower. This doesn't go on and on forever though, because as the weight, the weight stays the same. The drag will get bigger and bigger until that magical moment that you all know, we reach a position where the forces exactly balance. Now, that's a special position because at this point, the resultant is 0 because the force downwards is equal in size to the force upwards, which means the acceleration also at that moment has to become 0 meters per second squared, because remember F equals ma, whatever the mass of the parachutist, if the force acting on him is 0, the acceleration will be 0. So this line, in fact, levels off, and then the person will move at a constant velocity in this region here, and that velocity, if we read it off the graph, let's call it Vt. This is the terminal velocity. I'm still checking the chat, so if there's something I say which you want me to go through again, just flag it in the chat and I will, without saying anything. I'll adapt seamlessly to your suggestions. You'll never know it's happening. So that's terminal velocity. Now, unless a common extension to this is when, you obviously don't want to die by hitting the ground too quickly. So what happens next, usually, is parachute opens. Now, when a parachute opens, again, the weight stays the same. So the weight, unless the parachutist vomits, his weight will remain the same. The drag, once you open the parachute and it's actually open, the drag will increase like this. So you'll have a massive increase in drag. The resultant force, therefore, is upwards. That does not mean the parachutist moves upwards. Remember, they're moving downwards at terminal velocity, like 45 meters per second or something like that. When the parachute opens, they don't just suddenly move upwards, they slow down. So what will happen is you'll get a slowdown like this. So the graph, look at the graph I've just added to the graph. They'll slow down suddenly. As they slow down, what happens to the drag? Well, as they slow down, because of this new large drag force, that large drag force actually gets lower and lower as they slow down. So they do slow down, but not as much. And then eventually the drag balances the weight again, only this time, instead of increasing to balance the weight, it reduces as the person slows down until a new terminal velocity is reached down here. So it's almost the same process as in this first bit, but the other way around. So the parachute opens, the drag force is very big and then gets smaller and smaller until it balances the weight while the parachutist is slowing down. So this is also a region at which the parachutist reaches a new terminal velocity. Now, in answering questions to do with this, use terminology. You will almost get marks for using terms like resultant force, acceleration, terminal, velocity, weight, so drag. So always focus, and I'm sure Mr. Bagley says a similar thing when he's talking about whatever photosynthesis questions or like whatever. Use terminology. Try to be, don't waffle unless you really want to just, unless you really don't know something and then you're trying to get marks. Try to be concise and use terminology because that's what you'll get marks for. If you look at mark schemes, although mark schemes aren't brilliant, it shows how quickly you can rack up marks by saying the right thing and using the terms of relevance. Can I just go back actually, because I remembered this equation is, in fact, you know what? I'm sure when I teach force motion sometimes, I actually leave this equation until the end of the year because I don't want to sort of well, it causes needless confusion. But let me just talk about it a bit more. So if I had a situation, just to tell you how you might use it, if you had a situation where I gave you an initial speed, 10 meters per second, gave you, I don't know, a final speed as well, let's say 50 meters per second, and then told you what distance the car had traveled. Right, they'd done that in 20 meters. So you might think, and then I said, what's the acceleration? Some of you would think, oh, I've got an initial and final speed. Oh, well, you use A equals V minus U over T. Yeah. So let's use that, A equals V minus U over T. But then you look at the information you're given and think, right, I've not got a time. So how am I going to do this? Well, that's when you would use V squared equals U squared plus 2AS, because you've got V, the final, you've got U, the initial, so that's U, V, that's U, and you've got S. So you could use that equation to work out what A is, given that information. Now, I'm not saying that's the only way to do it. If you're some of you might be able to see, if I tell you it's constant acceleration between here and here, between here and here, you might be able to see a way of coming up with an answer for the acceleration. But the simplest way is just to use this equation. So you'd have 50 squared equals 10 squared plus 2a times 20. Okay, now I've started, I might as well finish it off. You couldn't use, for this, a question, you couldn't use A equals V minus U over T because you don't have a time. Right, to use A equals V minus U over T, you need to know how long it took for the speed to change. So you have no alternative but to use the one involving V, U, A, and S. So what does that give us? 50 squared minus 100 divided by 40. 60 meters per second squared, I think. Okay. Next. So that, believe it or not, that more or less, that summarizes the content of the removes forces section. You will remember that, you took hash time to sort of do, there were demonstrations. It takes time to just get comfortable with these concepts. Now you look back at them, having done more physics, you probably think, actually, it's not that much that you need to know. I suppose that the thing you need to do now is practice doing questions on it so that you can recall it easily. Okay, it's one thing listening to me in a session and thinking, oh, I've done revision, but this isn't revision. Okay, thank you. If you have to leave, that's fine. I'd just let me have a 30-second rant. These sessions that Mr. Bagley and I put on are not revision. It's useful, I'm sure, and I hope it's useful, and I'm sure that it's something to do with nothing else. But you can't just come to these sessions and think, right, I've revised now. What you need to do is look through the material yourself, try and remember it, test yourself on it. Right, I'm not going to redo the Elevate lecture, right, because you really don't want that. But don't think the work's done coming to listen to me talk for an hour. Right, continuing. So we've got motion, we've got basic forces. Next, moments. So I'm doing this in roughly the same order you would have come across it. Now, moments a moment is a term which means the turning effect of a force. So moment is a turning effect of a force. Does it cause rotation? Now, the equation to work out the moment of a force, you take the force and you multiply it by, now, I should have drawn the diagram first, shouldn't I? What's called the perpendicular distance from the pivot. Now, I'm going to steal an example from an exam paper. I wonder if I can remember. I'm going to guess the year. I think this is June 2011. Right. If I'm right, that's like sad. A laptop. If you want to close the lid of a laptop, and since you've all got one in front, well, you've probably got one maybe in front of you. It's easiest to close if you push at the top perpendicular to the lid. It's much harder to close if you try to close it harder to the hinge. You need to apply a much larger force to get it down. If you pushed at the bottom, now who would do that? Equally, if you try to push the laptop like this, again, why would you do that? That wouldn't help. That would make it harder to close. You would need to apply a larger force in this direction to actually close it, because the perpendicular distance would no longer be this. It would actually be, it would have to be that you were taking, which is shorter. Now, don't worry too much about perpendicular distance, okay? I would always write it, like always write this bit, like don't just write distance. Always write the full perpendicular distance from the pivot, but you should have some familiarity with what it means. And it means that the force, whatever line connects the pivot to where you apply the force arrow has to be at 90 degrees to that line, right? In order for you to use that distance to calculate the moment. Now, you'll be pleased to know that at IGCSE, almost always the force is in that direction, okay? So that makes things simple. You just do force times distance. Okay, so typical, let's do a question, because it ticks two boxes, this one. The way moments are asked about is in the context of equilibrium. So in order to be in equilibrium, we've already said the forces have to be balanced, right? This object will remain at rest or constant velocity unless acted upon by a resultant force. This is basically describing what's called equilibrium. So that's a good term to remember, right? Equilibrium just means at rest or at constant velocity, force is balanced. But in order for equilibrium to actually hold, you also need to have no net moment as well. Because consider this: if I put a box here, which has a weight of 50 newtons, and it's 2 meters away from the pivot, and I put another box, right, don't draw this if you are. I'm going to put another box here, 50 newtons. And let's say that this is 1 meter away. Actually, no, let's make it a different way. So let's make it 30 newtons. And this is an unknown distance, right? So let's call it D. There is something called the principle of moments. And again, to slow myself down and so that you can fully digest what it is, I'm going to write it in full. So this is a 2 marker. What's the principle of moments? It is the sum of clockwise, or the clockwise, why am I leaving out the article, moments is equal to the sum of the anti-clockwise moments for a system in equilibrium. Okay, so 1 mark, sum of the anti-clockwise moments is equal to the sum of the anti-clockwise moments. 2nd mark, for a system in equilibrium. Okay, so both of those things you need to include if it says 2 marks. Let's use it here for this situation. Again, this is a revision, a sort of, okay, I will. Revision session, I'm going to try and do the sort of basics. You can obviously get more complicated examples, not much more complicated, but this is a sort of good compromise. What you do is, I would, on one side, you know, you can kind of have an equal sign. On one side, I would have the clockwise moment, or the clockwise moments, and on the other, have the anti-clockwise moments. And then you could say, well, the clockwise moment is going to be due to the 30 newtons here, because it's going to be rotating that way. So the clockwise is going to be 30 newtons times by our unknown distance d. And that has to be equal to the clockwise, the anti-clockwise moment, which I'll do in a different color. Let's do it in orange. The anti-clockwise moment, which is due to the 50 Newton force, which tends to bring us anti-clockwise. So the value of that would be 50 newtons times by the distance, 2. So we get 30 d equals 50 times 2 is 100. So then d is 100 divided by 30, which is 10 over 3, which is 3 1/3, which is 3.33 meters. So you're basically working out the clockwise moment or the anti-clockwise moment and then setting equal to the anti-clockwise moment. I've just, again, let me just go back to this, because this is something that is asked about and can cause confusion. Perpendicular distance. Let me just give you 2 drastic, shall I use a different example? Let's use a spanner, right? So if I used a spanner to take, loosen a nut or a bolt or whatever, a nut, then if you, let's say we chose several ways we could apply the force. In that direction, F1, and in, let's say we pushed it that way, F2. Okay, so those are 2 ways you could push the end of the spanner. You might, well, I could ask, if this were a normal lesson, I'd probably, we can have a vote, okay. But I'm going to save time by not doing that. I could ask, and you can think to yourself, like, which is more appropriate, which is going to be more mechanically efficient. And I would have thought, just intuitively, most people would say F1, just because you can imagine using a spanner and you know that pushing vertically downwards would give you the most torque to like undo the bolt, whereas pushing sort of off in like towards the bolt in any way kind of is wasting force, in a manner of speaking. So F1's clearly better, or it is better. Why is that? Like, because you might think, oh, they're the same distance from the pivot, because look at the pivot is here, and the force is acting at the other end. So you think, oh, the distance is just the length of the spanner, isn't it? Like this, for both forces. So the moment's the same, F1 times D and F2 times D, but it's not, because this distance, you see the line through F1, the vertical line, which I'm going to shade in yellow here, this vertical line, this direction. This distance is measured perpendicular to that force arrow direction. If I were to draw the same imaginary line through F2, the distance D, which I'll draw again down here, this distance, it's at an angle, right? It's not at 90 degrees to that line through F2. So you can't actually work out the moment of F2 using distance D. What you actually would need to do, and you don't need to do this at IGCSE, is work out what that distance there would be, because that distance would be in a direction which would be at 90 degrees perpendicular to the line going through F2. It's called the line of action of F2. So I'm happy to answer questions on that further, because I'm sure in some cases that's still not entirely clear, but can I reassure you that you will not have to do a calculation where you have to worry about what distance, like an angle do I need to use, right? It would only be ever used in a sort of descriptive way, like F2 is not as efficient because the perpendicular distance is shorter. Right, you can stay behind or email me afterwards if you want me to go through that a bit more. So that's the headline points of moments. Next, pressure. So, in fact, let's not do pressure because you've kind of recapped that recently. Momentum, that's always one that people want to go through. So, momentum. You first come across momentum and use the term when, I suppose, when you think of like big objects moving, you sort of think, oh, you know, that rugby player has a lot of momentum when they're moving quickly and they're stacked. Or like that lorry bombing along has a large momentum. That's with good reason, because that's what momentum is a measure of. It's a combination of mass and velocity. If a fly were to fly into my forehead at 1 meter per second, it's clearly going to have a different effect on me than if a golf ball hits me in the forehead at 1 meter per second. So that's what momentum's all about, quantifying that kind of physicality, right? So momentum is simply the mass of an object times by its velocity. Could you think, apart from adding, right? Apart from adding, you can't think of a simpler way to combine two quantities, just multiply them. Let's talk units. So mass, SI unit kilogram, velocity, meter per second. You just stick them together. Units, you can just work out from equations. You just stick the units together, the kilogram meter per second. And it looks, when you first come across it, you think, oh, that looks a bit bizarre, just sticking two units together, but that's the unit. There's no problem with that. Now, so you could work out, for instance, you know, if an object's moving at 2 meters per second and it's got a mass of 5 kilograms, then its momentum, which is lowercase p, so momentum is lowercase p, is going to be m times v, which is 5 times 2, 10 kgm per s, 10 kilogram meters per second. So that's how you use the equation. Just like for moments, we've got a principle of moments. For momentum, we also have a principle which we can use to do calculations and work out stuff about situations. And that is the principle of conservation of momentum. And again, I'm going to write it in full. Sometimes I think at IGCSE, it's easy to think, God, this is what, like, so what, right? What's the importance of this? Well, the principle of conservation of momentum and that other big conservation law, the one to do with energy, put constraints on what can happen. Like, not just anything can happen in the universe, right? You know, it puts constraints on what's allowable, and that affects chemical reactions, which affects biology, right? Which affects, you know, our lives. So, you know, and sort of it affects everything. So these principles, although they sort of on their own, they appear very dry and just like, I don't know, mathematical, they're important. So another 30-second rant. Principle of conservation of momentum is well, there are two ways of stating it. Usually you'll see it quoted like about before and after a collision. So you can say the total momentum before a collision. I prefer, to be honest, an interaction, but you most often see collision, is equal to the total momentum after a collision, part 1 mark, provided that no external forces act. I don't know why I'm switching between capitals and lowercase. So these are the two bits you need for conservation of momentum. Total momentum before, total momentum afterwards equal, and then you need that bit on the end, provided that no external forces act. Because as soon as you start interfering with the system by prodding it and applying forces to it, all bets are off. Now, if that's what you most see often in exam papers, but another statement or an alternative is the total momentum of an isolated. This is the sort of technical one, but I like it because it's concise. The total momentum of an isolated system is constant. Why not, Edexcel, just have that as the standard definition? Because it says what the above statement says, right? The total momentum is just constant through time, before, after, right? And isolated system means no external forces are acting on it. It's isolated from its surroundings. So that statement, that bottom one, I'm sure you can appreciate, is nice, right? It's concise. So let's do an example. Oh, what should we do? Well, let's just do two balls colliding, right? So first one's at rest, 200 grams. And then we've got, let's have a 300 gram ball moving at 10 meters per second. And let's say they stick together, right? So this is before. And then afterwards, let's say that they've stuck together, they've kind of, what's the word? Coalesced. And then they move at speed v. So the question is, if these two balls, which stick together and then move off together, collide, what's going to be the speed afterwards? So I would, first of all, think, right, the momentum before has to equal the momentum afterwards. So what's the momentum before? So the momentum before is equal to, well, we know that momentum is mass times velocity. So we've got now I'm going to convert the 300 grams into kilograms, remember, because I want my momentum really in kilogram meters per second, but it's not necessary, but I'm going to do it here. 0.3 times by the speed, which is 10. So this is for this mass. And then the other one is at rest, isn't it? The speed is 0. So the momentum is also going to be 0. So we don't really have to write anything for that one. So 0 momentum. So that's the momentum before 3 kilogram meters per second. And that has to equal the momentum afterwards though, doesn't it? So the momentum afterwards is going to be the mass of this combination. Now, provided that no mass is lost, this is going to be, okay, we'll do that as well. 500 grams. So we'll get 0.5 because 500 grams is half a kilogram times by V. But we know that that has to equal the 3 kilogram-meters per second we had beforehand, because of the principle of conservation of momentum. So V is therefore going to be 3 divided by a half, which is 6 meters per second. So it's an example of a physical law, the conservation of momentum, putting constraints on what happens in the universe, right? Those are the rules of the game. That's one of them, conservation of momentum. The only velocity that object can have afterwards is 6. Now, another type of question, which I've been reminded of, is where you've got objects moving apart. So, you know, when you fire a gun, you get a recoil. So the bullet moves that way, but you feel it force backwards. Let's use the example that's been suggested to me. In fact, this has happened to me. Yeah, this has happened to me before, sadly. If you are in a boat or on something similar to a boat on water and then try to step out of it and move this way, you push back on the boat, don't you? Like, imagine the boat's in the water and then you step out onto quayside. If the boat's not secure, you push yourself off the boat and then the boat moves backwards. So let's say that we've got a person in a boat at rest. The boat weighs 100 kilograms and the person weighs 60 kilograms, right? So there are 2 objects at rest. So let's say the person tries to step out. So the person pushes off, accelerates themselves, and gives themselves a velocity of 1.5 meters per second. Right? So they're almost running off. Well, yeah, they're just walking briskly off the boat. So they push off. So I'll put their leg in contact with the boat, right? So they're pushing off the, let's redraw that, in fact, because you want them to still be sort of pushing off. So they're pushing themselves forward, giving themselves a velocity of 1.5 meters per second. The question is, the boat's going to move backwards, but with what speed or with what velocity? So V question mark. We do the same thing. So we say, what's the momentum beforehand? So the momentum beforehand, well, they're both at rest. So the momentum before is 0. No momentum, neither are moving. What about afterwards? So the man has a momentum to the right as we look at the diagram, doesn't he? The momentum afterwards is going to be the momentum of the man, which is 60, his mass, times by 1.5. So this, I like these highlighters, this is good, right? So this term is for the man, right? But what about the boat? Well, we don't know necessarily what the boat, we don't know the boat's velocity, do we? But we know its mass. So what I'm going to do is just add 100, the mass of the boat, times by whatever velocity it has. Right, we don't know what V is. So, but then we know that the total momentum afterwards has to be equal to what it was before, which was 0. So if you write that out, 60 times 1.5 is 90. And then we've got plus 100 lots of V equals 0. So then if we rearrange that, we get 100V equals, we subtract 90 from both sides. And so we get V is minus 90 over 100, which is minus 0.9 meters per second. So it does move. You see how that minus sign crops up? So what this minus sign tells us is that the velocity is in the opposite direction to the man, because by putting his velocity as just positive 1.5 here, what we've done is we've basically chosen this direction to the right to be our positive direction, so that when we then do the calculation and work out a value of V for the boat, we get a negative sign, which means the boat is moving backwards or in the negative direction. Now, again, that is a situation which rarely crops up, okay? But it's worth knowing, it's worth being aware of and thinking about. So, you know what, when I said before, you can't just listen to me talk through about this stuff. I mean, it helps and it acts as an aid memoir, but you need to sort of sit down with this and think about it yourself and try and work it out. Look up YouTube videos explaining it. And then once you've done that and still don't understand it, come and ask specifics. Okay, so I'm not expecting people to walk away from here going, wow, oh, I can get that myself now perfectly. I mean, this is almost the groundwork, right, for the revision you're going to do. Oh, so the test on forces of motion will be given to you at some point next week by your bigs. So either for Banco, in which case it won't really be a test. I mean, is it a test anyway if you do it in Hash online, or in Hash at some point? You can, as long as you're polite, you can ask them when they're intending to set it. I'm going to try and make these sessions like this session's for force of motion, then next week's session will be for the next one, which is electricity. So I'll try and keep them in sync. I've still got a few minutes to use. So motion forces, moments, momentum. Okay, let's mention pressure because pressure comes under force, okay? So let me do this as a little spider diagram. With pressure, and of course you've revised pressure recently because you've talked about gas pressure. But pressure, there are three sort of regimes or situations where you come across it. There's normal pressure, the basic definition is force divided by area. Right, so pressure is force divided by area. Now that's true of any pressure, liquid pressure, gas pressure. That's at its heart, that's what pressure is. How much force is applied per unit area. It doesn't matter if it's a solid, liquid, gas, that's what pressure is. The units, okay, so the units are pascals, newtons, and meters squared. That tells you also that a Pascal, what the meaning of a Pascal is that it means that 1 Newton is being exerted over every meter squared of area. So in some way, newtons per meter squared, again, I often talk about this with my class. Some units obscure what the actual quantity means. So if you said newtons per meter squared, you'd know it was a force per unit area. Whereas Pascal doesn't really tell you that information, does it? But you should know the unit is the Pascal, so P-A-S-C-A-L. Now, although pressure equals force over area is useful and is the definition of pressure, when we've got liquids and gases, there are other equations which allow us to do calculations with pressure. The one that you remember, well, the one that you covered in the removes, for liquids, pressure, and it's really pressure difference, equals depth times density times our friend, the gravitational field strength. Oh, in fact, I've just remembered something, which I'll come back to. P equals H rho G. That is actually derived from pressure equals force over area. When I teach this equation, P equals H rho G, you actually use pressure equals force over area, this equation here, to get to that one. So it's really P equals F over A in disguise, but even though it doesn't look like it. So that's within a liquid. And then you've done gas pressure recently, so I'm not going to talk about, have a separate bit of writing for that. The thing I forgot, gravitational field strength. you also cover this up here, right? So in forces, G, right, the value of G, gravitational field strength. Now this is quite important. Some of you will have still not be happy with this sort of what I'm about to say. Gravitational field strength. This tells us how many newtons every kilogram of weight feels on Earth. So remember W equals mg, right? That's another equation you need. Weight measured in newtons, which is just a force, is a mass, kilograms, times by G. Now, you probably remember G to be in newtons per kilogram, right? So you say on Earth, 9.8 or 10, or well, at IGCSE, 10 newtons per kilogram, right? You say, oh yeah, G on Earth is that. And that's fine, right? It tells you how many newtons each kilogram of mass, how much force each kilogram of mass feels. But some of you will also have seen this. G equals 10 meters per second squared. You'll have heard it called the gravitational, or the acceleration due to gravity is probably the better way to put it. Now, they're the same thing. They're just two different ways of writing the unit. And it's just a different name, because look at this, right? This might actually clear something up for some of you, which you've wondered. You know the equation F equals ma, right? W is just a special type of force. And then mass is mass. And then this G is basically an acceleration, right? W equals mg is just F equals ma, just for objects on Earth, like near the Earth, right? G acts as an acceleration, of course it does. So the equations are basically the same thing. The reason why acceleration in newtons per kilogram are the same unit, rearrange this. A equals F over m. What did I say about units? If I have newtons divided by kilograms on this side, and then we know the unit of meters per second squared is the unit of acceleration, that means the meter per second squared is the same thing. It's the same unit as the newton per kilogram. It's just two different ways of writing the same unit.